Hello everyone. Welcome to Subnetting a little bit. Today we will take a look at VLSM subnetting. We'll show a comprehensive or rigorous approach to ensure you understand the details. Later in the series we'll use a reference chart to speed up the process. This table shows the difference between FLSM, or traditional subnetting, and VLSM subnetting. The fundamental difference is that VLSM is more efficient and considerably less wasteful in terms of the number of addresses consumed. Take a little time to review the table. To illustrate the difference in efficiency, let's use this topology to set up a traditional subnetting scheme based on the number of hosts. We use the total usable formula and set it equal to the largest subnet. This will give us over 8,100 addresses per subnet, or more than 32,000 usable addresses between the four subnets. However, we only need 9,750 addresses. This produces an excess of just over 23,000 addresses that are being consumed but will not be used. They are essentially wasted. On the other hand, VLSM, which is always based on the number of hosts, optimizes the number of addresses per subnet based on the requirements. VLSM applies the total number of usable addresses formula, h² - 2, to each subnet. In this topology, note the number of addresses consumed in each subnet. In total, it consumes just over 13,000 addresses. But we only need 9,750, so the excess is 3,618. The excess with FLSM was just over 23,000. Using VLSM instead of traditional subnetting saves almost 19,400 addresses. In a small network, conserving addresses is irrelevant, and using FLSM is fine. Address conservation is more of a concern on large networks. Let's begin our VLSM example. This is the topology. We will use VLSM to create subnets meeting the requirements stipulated, including the serial link. We will use this table to help us. It embeds the process within the columns. We will work top-down and left to right. First, we list the subnets in order from largest to smallest. We start with the production subnet, which requires 6,000 hosts. Engineering requires 3,000. Corporate calls for 100. The branch office needs 50. And finally, we need 2 addresses for the serial link. Next, we need to determine the number of host bits required for each subnet. For the production subnet, we need 6,000 usable addresses. Using the power of 2 table, we see that 13 host bits satisfies the requirement. The engineering subnet needs 3,000 addresses. The table shows we need 12 host bits. For 100 host addresses, we need 7 host bits. For 50 usable addresses, we need 6 host bits. And finally, for the serial link, we need 2 host bits. Since we are subnetting a Class B address, let's go ahead and place 2 uppercase N's for all address maps. Similarly, let's record the value of the Classful octets in the addresses as the will not change. Going back to the production subnet address map, let's record 13 host bits. Then backfill with enough subnet bits to account for 32 bits. We'll do the same for the engineering subnet address map. Record 12 host bits and backfill with 4 subnet bits. For the corporate subnet, record 7 host bits and backfill with 9 subnet bits. Repeat the process for the branch office subnet. 6 host bits and backfill with 10 subnet bits. And finally, for the address map of the serial link as well. Record 2 host bits and backfill with 14 subnet bits. This allows to account for a total of 32 bits. Let's look at the subnet mask for the production network. Note the original given address and the subnet address map. For the subnet mask, set all network bits to 1. Recall that subnet bits are network bits, so we set those to 1 as well. Then set all host bits to 0. This gives 255.255.224.0. Repeat the process for the other subnets. Engineering, corporate, the branch office, and the serial link. Moving on to the wildcard mask. It is the inverse of the subnet mask. Once again, let's consider the production subnet. The table shows the original address given to subnet, along with the address map. For the wildcard mask, set all network bits to 0. Since subnet bits are network bits, we set those bits to 0 also. Then set all host bits to 1. This gives 0.0.31.255. Now determine the wildcard mask for the other subnets. Engineering, corporate, the branch office, and the serial link. Now we come to the prefix length. The prefix length is simply the total number of network bits. The subnet address map for the production subnet has 19 network bits, so the prefix length is /19. The network portion of the address map for the engineering subnet has 20 bits, so the prefix length is /20. For the corporate subnet, we have 8 plus 8 plus 8 plus 1, giving us 25 network bits, producing a prefix length of /25. The address map for the branch office shows 26 network bits, so the prefix length is /26. And finally, the serial link only has 2 host bits, so it must have 30 network bits, giving us a network prefix of /30. As we proceed to the interval and transition octet, we will show 2 ways of obtaining these values. Method 1 uses the subnet address map. We've been using this method throughout the series, so it should be familiar. Method 2 uses the subnet mask. Let's use both methods on the production subnet. Using the address map, identify the place value of the rightmost subnet bit within the octet. The place value of the rightmost subnet bit is 32. This is the interval, 32. Since it resides in the third octet, this is the transition octet, octet 3. For method 2, we'll perform a simple analysis of the subnet mask. The transition octet is the rightmost non-zero octet in the subnet mask. Octet 3 is the rightmost octet that is not a 0. Therefore, octet 3 is the transition octet, To determine the interval, subtract the value in the transition octet from 256. In other words, 256 minus 224 equals 32. This is the interval, 32. Some publications refer to this value as the block size. Let's use the subnet mask method for the engineering subnet. The rightmost octet in the subnet mask that is not a 0 is octet 3. This is the transition octet. It has a value of 240. Subtracting 240 from 256 gives 16. In other words, 256 minus 240 equals 16. The interval is 16, and octet 3 is the transition octet. Using the address map method for the corporate subnet, take a look at the subnet address map. The place value of the rightmost subnet bit within the octet is 128. And it resides in octet 4. So for this subnet, the interval is 128, and octet 4 is the transition octet. Using the subnet mask method for the branch office, note that octet 4 is the rightmost octet that is not a 0. This means octet 4 is the transition octet. To determine the interval, subtract 192 from 256. That is, 256 minus 192 equals 64. The interval is 64, and octet 4 is the transition octet. Let's use the subnet address map method for the serial link. The rightmost subnet bit in the address map resides in octet 4. And its place value within the octet is 4. This means the interval is 4, and octet 4 is the transition octet. Let's move on to the addresses column. We'll determine all the network addresses first. The value of both classful octets has already been recorded as 172.16. We will then proceed to determine all broadcast addresses, followed by the first usable address in each subnet, and finally, the last usable addresses. For the network address of the first subnet, use the given address to subnet and apply the prefix. This gives 172.16.0.0/19. To determine the next subnet, the engineering subnet, we will use the interval, transition octet, and network address of the previous subnet. Add the interval of 32 to the transition octet, octet 3. Then set all host bits to 0. This gives 172.16.32.0. Then apply the prefix of /20. Once again, to determine the third subnet ID, we need the interval, transition octet, and subnet ID of the previous subnet. Add the interval 16 to the transition octet, octet 3. Set all remaining host bits to 0. Then apply the prefix of /25. For the fourth subnet ID, we need the interval, transition octet, and subnet ID of the previous subnet. Add the interval 128 to the transition octet, octet 4. Then set all remaining host bits to 0. In this case, since octet 4 is the last octet, there are no remaining host bits. Now apply the prefix length of /26. Repeat the process for the fifth subnet ID. Add the interval 64 to the transition octet, octet 4 of the fourth subnet ID. This gives 192 in octet 4. Then apply the prefix of /30. Let's work on the broadcast addresses. We will use the method where we add the wildcard mask to the network address. To identify the broadcast address for subnet 1, add the corresponding wildcard mask 0.0.31 172.255 to the network address of 172.16.0.0. This gives a broadcast address of 172.16.31.255. For broadcast 2, add the corresponding wildcard mask 0.0.15.255 to the network address of 172.16.32.0. This gives 47.255 in the last two octets. For broadcast 3, once again, add the corresponding wildcard mask to the network address. This gives 48.127 in the two last octets. For broadcast 4, add the corresponding wildcard mask to the network address. This gives .191 in the last octet. And finally, for broadcast 5, add the corresponding wildcard mask to the network address. This gives 195 in the last octet. Let us now determine the first usable address of each subnet. As we saw in the previous subnetting videos, simply add 1 to octet 4 of the network address. For subnets 1, 2, and 3, this gives a 1 in octet 4. For subnet 4, we get 129 in octet 4. And for subnet 5, we get 193 in octet 4. Turning our attention to the last usable addresses, we subtract 1 from octet 4 of the broadcast address. For subnets 1 and 2, the last octet is 254. In subnet 3, the last octet is 126. The last octet in subnet 4 is 190. And finally, for the last subnet, the serial link, we get 194 in the fourth octet. That's it for now. Thanks for watching. And remember, nothing worthwhile comes easy. So go forth and subnet a little bit.